Welcome to EPG Pathshala. In this tutorial, we will be discussing two very important concepts. One is called Randon-Nikodym derivative or Randon-Nikodym theorem, and second one is called Lebesgue decomposition for measure. Before going into these concepts of these two, we need a few definitions which are very important. We know measure, we have learned the different properties of measure, and we have spent a few slides on measure only. So now we will define a few new things. What do you mean by sigma finite measure? What do you mean by finite measure? What do you mean by singular measure, absolutely continuous measure? So in this tutorial, I will try to describe all these notations or all these notions that will be required for understanding Randon-Nikodym derivative and Lebesgue decomposition for measure. Once we have these definitions, then we will go to the theorems, and before going to the Randon-Nikodym derivative or Randon-Nikodym theorem, we will have to mention a few more theorems too. I will try to describe those without going to the nitty-gritty details of each and every theorem. Then how we can use this Randon-Nikodym derivative, that will also be discussed. Finally, this tutorial will be concluded by describing what do you mean by Lebesgue decomposition for measure and how we can use it to find decomposition or to find the expression for any distribution function, capital Fx. In this module, we will describe two very important theorems. One is called Randon-Nikodym theorem, and the second one is very important, Lebesgue decomposition for measure. Before going to the details of this theorem or this decomposition for measure, we need a few definitions. What do we mean by sigma finite measure, singular measure, absolutely continuous measure? So we will start with the definitions of this. Once we know the definitions, then we will define or we will state Randon-Nikodym theorem and its application. Finally, we will be discussing what do you mean by Lebesgue decomposition for measure. So we will start with finite and sigma finite measure. Consider the measure space omega, script f and mu. So this is the measure space where mu is the measure. A measure mu is said to be finite if mu s, measure of any set belonging to that sigma field, will be finite. Mu s is less than infinity. A measure is said to be sigma finite if for every a belonging to script f, there is a sequence of sets an such that a is a subset of union over n from 1 to infinity an and mu an is finite. So each of the measures mu an is finite and a is a subset of union over n from 1 to infinity an. Specifically, if we have a sequence of sets an with omega is union over n from 1 to infinity an and mu an is less than infinity, we say that mu is sigma finite. So finite means mu s is less than infinity and sigma finite means that we need to have mu an less than infinity and omega equals to sum over union over n from 1 to infinity an. Now we have one very interesting result, that every finite measure is sigma finite, but the converse is not always true. We don't mix up with the concept that we have got in case of sigma field. We know that if it's a sigma field, it must be a field, but not all fields are sigma field. Here, if it is sigma finite, then we are not very sure that whether every time it will be finite or not. We will give one counter example. Now we take one example. Suppose this is the probability measure. We are taking p. P is the probability measure and we know it is finite. And it is sigma finite because all finite measures are sigma finite. Now consider the measure space 0, 1, and using this 0, 1, we have this Borel field B, script B 0, 1. And lambda is the measure. Suppose lambda is a finite measure. That means lambda is also a sigma finite measure. Now if we take one counter example to show that it is sigma finite but it is not finite. So we consider the triplet script R, script B and lambda, and we define lambda AB as B minus A, length of the interval. Now if we take A as minus infinity, B as plus infinity, that means if we take lambda R, lambda is not finite. So this is not finite. But if you see that R can always be expressed, the real line can always be expressed as union over minus infinity to infinity n plus 1. So if we do this, then I can write R as union over an, where n belongs to the natural numbers and an is an interval n plus 1. Now if I define, as we define lambda AB as B minus A, then lambda an will be n plus 1 minus n, that is equals to 1. So lambda an is equals to 1. This is finite. So thus lambda defined on RB is sigma finite, but such lambda is not finite. So this gives the counter example which says that even if it's a sigma finite, it may not be finite, because we have already shown that lambda R is not finite. Lebesgue measure is sigma finite. This is another example. Now consider the triplet R, B and nu. R is a real line, script R is a real line, B is the Borel space and nu is the measure, and we define nu A as the number of elements in A. Such nu is not sigma finite. So in generally speaking, counting measure defined on measurable space is not sigma finite. Now we will define two very important terms, singularity and absolute continuity. So let mu and nu be two measures defined on measurable space omega and script f. Mu is said to be singular with respect to nu, and vice versa if there are sets A and B belonging to omega such that A union B is omega and A intersection B is phi. That implies mu A equals to mu B equals to 0. If this happens, then we will say that mu is singular with respect to nu, and we are putting a notation that nu, something like orthogonal notation, mu orthogonal mu. So this is the notation we will be using to define singularity. Nu is said to be absolutely continuous with respect to mu. We denote it as nu less than mu, that is mu is dominated by nu, if there exists a set A belonging to script f with the property that if mu A equals to 0 implies nu A also equals to 0. Let f be a non-negative measurable function on omega, that is f greater than equals to 0, and f inverse b belongs to script f for every b belongs to the Borel field and whenever f is real valued. Then we set nu A as integration over A f d mu for every A belongs to script f. It can be easily seen that nu will generate a measure on omega script f because it is satisfying all the properties of a measure. For example, nu A greater than equals to 0 for every A belongs to script f, nu phi is equals to 0, and nu union over I from 1 to infinity ai is integration over infinity I from 1 to infinity ai f d mu is equals to I from 1 to infinity nu ai whenever ai's are disjoint, and it can be seen that mu A equals to 0 implies nu A also equals to 0. Now we have the theorem called Randon-Nikodym theorem. It says that let mu and nu be two sigma finite measures and nu is less than equals to mu. That means nu is absolutely continuous with respect to mu. Then there exists a non-negative measurable function f such that nu A is integration over A f d mu for all A belonging to the script f. Further, f is unique almost everywhere related to mu. That is, if nu A is equals to A h d mu, this is another function, then f is equals to h almost everywhere related to mu. We know the concept of almost everywhere. That means if this doesn't hold for that particular set, the measure of that set will be equals to 0. This is the concept of almost everywhere. So, and this f is called Randon-Nikodym derivative or density. We defined f as d nu by d mu. Now we will give one simple example. Suppose we have a measurable space real line and Borel sets. We define nu, the measure minus infinity to a is 0 if a is less than 0, and this is equals to 1 minus e to the power minus a if a is greater than or equals to 0, and mu is Lebesgue measure. Now we know that whenever a is less than 0, nu minus infinity a is equals to 0. So by definition, integration over minus infinity to a 0 d mu, that implies f a equals to 0 whenever a is negative. Well, when a is positive, whenever a is greater than 0, nu minus infinity a is equals to 1 minus e to the power minus a. We can get this result if we integrate it over 0 to a f d mu and we take fx as e to the power minus x. That means fa is e to the power minus a for all a greater than or equals to 0. Hence d nu by d mu will be f. This is the derivative we are talking about. Now how to show the uniqueness? Now suppose I am defining a as f equals to 0 if a less than or equals to 0 and e to the power minus a if a is greater than 0. Similarly, I am denoting h equals to 0 if a is less than or equals to 0 and e to the power minus a if a is greater than or equals to greater than 0. Then if I take the set for which f is not equals to h, that is mu of collection of a such that f a not equals to h a, I don't have any such member. So mu of phi and mu of phi equals to 0. So it shows that this is unique too. Now we will define very important result called Lebesgue decomposition for measure. The theorem says let mu and nu be two sigma finite measure on omega and script f. There exists two sigma finite measures nu s and nu a such that nu a less than nu, that means nu a is absolutely continuous with respect to mu, and nu is singular with respect to mu, and nu can be written as nu a plus nu s, and the measures nu a and nu s are unique. The subscripts a and s, they have some meaning. A means absolutely continuous and s means singular. To prove this, consider the sigma finite measure lambda equals to mu plus nu. Note that lambda is equals to 0 implies mu e and nu e both are equals to 0. Then we can use Randon-Nikodym theorem. We may get two non-negative functions f and g such that for every a belonging to the script f, mu e is equals to integration over e f d lambda and nu e is integration over e g d lambda. Now take the set A as f greater than or equals to 0 and B be another set f is equals to 0. Since f is non-negative, then you say omega is A union B and A intersection B is phi, mu B is equals to 0. Now set nu s for the singular part, nu s E as nu of E intersection B and nu A E is equals to nu of E intersection A. That is integrating over E intersection A g d lambda. Note that nu s A is equals to 0, so nu s is singular with respect to mu, and it can be seen that nu is nothing but nu a plus nu s. Now we are left with, we need to show that nu a is absolutely continuous with respect to mu. So let us assume that mu e is equals to 0, then integration over E f d lambda is equals to 0. Since f is non-negative, f is equivalent to 0 almost everywhere related to lambda on E. Since f is greater than 0 on E intersection A, this compels that lambda E intersection A must be equals to 0. Thus, nu AE is equals to integration over E intersection A d lambda is equals to 0. Now this is the decomposition we have, we call it as Lebesgue decomposition. Now we can apply this Lebesgue decomposition in the case of distribution function. This distribution function we have learnt in our undergraduate courses. So f is the distribution function of x, we define an omega, script and p is the probability measure. Then we know that any distribution function can be written as a convex combination of a discrete part and a continuous part. So fx can be written as alpha f dx plus 1 minus alpha fcx. So alpha lies between 0 and 1. This is the convex combination. The distribution function fc for the continuous part uniquely determines the pc, this is the probability measure for the continuous part on Rb. That is, Rb pc gives a probability space uniquely determined by capital Fcx. And this pc is a sigma finite measure. Let lambda be a Lebesgue measure on Rb. By Lebesgue decomposition theorem, we can find two measures Ps and Pac on Rb such that for any A belonging to the Borel set B, PCA can be written as PSA plus PACA, where PS is singular with respect to lambda and PAC is absolutely continuous with respect to lambda. For every two sets E1 and E2 from B, with E1 intersection E2 is equals to phi and E1 union E2 is equals to the whole real line, we know that PS A intersection E1 is equals to lambda A intersection E2. So using Randon-Nikodym theorem, we can find a non-negative measurable function f on R such that PAC, this is the absolute continuous part, is integration over A f d mu, and we can write f as Randon-Nikodym derivative of PAC with respect to lambda. So dPAC by d lambda is my f, the derivative almost everywhere, and f is called the density corresponding to the absolutely continuous measure PAC. And note that here f satisfies this condition that f is greater than or equals to 0 and integration over R f dx is equals to 1. The probability measures PS and PAC can uniquely determine two functions, namely GSX, which is a probability function PS minus infinity to x, and GACX is PAC minus infinity to x. AC for absolutely continuous, where GSX and GACX are both non-negative, non-decreasing and continuous. With the property GS minus infinity, GAC minus infinity equals to 0, GS infinity is equals to beta and GAC infinity equals to 1 minus beta. We can have the following representation that FCX can further be written as convex combination of GS and GACX is beta GACX plus 1 minus beta GACX. If beta is equals to 1, that means the second part will not contribute. FCX will be FSX, distribution is singular. If beta is equals to 0, then the first part will not contribute, then we will have FCX as FAX, FACX is the absolute part, so distribution is absolutely continuous. So using all this, we can finally find the expression Fx as alpha Fdx plus 1 minus alpha Fcx. Further, this part can be subdivided as 1 minus alpha beta Fsx plus 1 minus alpha into 1 minus beta Facx. Finally, we can write it in the form alpha d Fdx plus alpha s Fsx plus alpha ac Acx with the constraint that alpha d plus alpha s plus alpha ac must be equals to 1. So this is the convex combination. So you got this result using Lebesgue decomposition theorem for measure. I hope this tutorial gives some knowledge or some idea about sigma finite, finite, singular and absolutely continuous measure. We have gone through the notation and the concepts of Randon-Nikodym derivative and how it can be used to find the Lebesgue decomposition for measure. We have discussed everything in a nutshell. Though this module is not exhaustive, it will give some idea for future reading. I think this is just the starting or the beginning to understand Lebesgue decomposition for measure or Randon-Nikodym derivative.